Stay focused. Section 5.4. Section 5.4 is inverses of functions. Okay, it's inverses of function. In this section, we want to learn about inverses of relations. Remember, we talked about relations a while back. Okay, a function is a relation where you have every x has a y, and you have these ordered pairs. Okay, we're going to talk about inverse functions and the horizontal line test. We're going to talk about finding the inverse of a function, how you actually do that. So let's start out with the definition. The inverse of a relation, so let R be a relation. The inverse of R, what's R? What's R? A relation. Good. A relation. Good. The inverse of R, denoted as R to the negative 1, we call this R inverse, okay? This is R inverse. Is the relation defined by switching the first and second coordinates of each ordered pair that is an element of R. So remember, a relation is a set of ordered pairs, A comma B, where your A and your B are real numbers. However, here, your inverse just makes the second coordinate the first and vice versa. Okay? So, that's this set. That's important to note. So the inverse of R is really this. You switch the first and second coordinates of each ordered pair that is an element of your relation. Okay? So, example 1, we're going to determine the inverse of the following relations, and then we're going to graph the inverse and state its domain and range. Okay? Tell me how, and this is pausing for a second and we're going to get to an example. This is just in general. When we're talking about a set of ordered pairs, what gives us our domain from the set of ordered pairs?
The x's.
The x's. And for the range, what gives us the range?
Y.
The y's. You got it. Very good. So I'm giving you an example 1. I'm giving you a relation which consists of these 4 ordered pairs. I'm asking you to write down S inverse. I'm asking you to write down S inverse. What is S inverse?
Is it switching the x's for the y's?
Is it?
For the x's?
Is it?
So would it be negative?
She's asking a question. First answer her question before you say what to do. She's asking a question. Do we switch the x's and y's?
Yes.
Yes. Okay, so now go ahead.
Wouldn't it be like -3, -1, 1, and 4?
Wait a minute. There have to be pairs.
So it's -3, -1, -1. And
I got it right. So the x's and y's are the same here. So when you switch, it's going to be the same. Go ahead.
1 and 0.
Oh, then 1 and 0, and then 4 and 4.
4, 4. Good. So that's S inverse. What's the domain of S inverse?
-3, -1, 1, and
4. Good. So it's the set. Let's make sure we're clear. It's the set consisting of -3, -1, 1, and 4. Good. What's your range?
This set consisted of -3, -1, 0, and 4.
Good. Not too bad. Very good. Okay. So now you plot the points because I just asked you to graph the inverse. So that's the same thing as saying you plot these points here. Okay. So we have 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3. Okay, so one point is -3, -3. Next point is -1, -1.
Yeah.
That point up there is -1. So right here. Then we have what? 1, 0. Then we have 4, 4. Good. So we sketched our graph. What questions do you have? Okay. So now let's look at another example. Sometimes your relation won't be given to you as a set of ordered pairs. You'll have to determine that based on the function that you're given. Okay? Yep. You go 1. So in part B, I gave us a function. We have y is equal to the absolute value of x plus 2. Y is equal to the absolute value of x plus 2. So in this particular problem, our relation is described by the given equation in x and y. It's described by the given equation here, and that's in x and y. Okay? The inverse relation, so note the inverse relation is the set of elements with x and y. What happens with the x and y? What do we do with them? We flip, right? We exchange them, right? With x and y exchanged in the equation. Good. So let's actually write this out in terms of a set. That means even though we're going to switch the x and the y, we still have ordered pairs, right? We have the pairs x comma y such that x is equal to the absolute value of y plus 2. That's our set. Remember, it's the set of all ordered pairs where we switch the x and y. So we just wrote down mathematically what we said already. So again, it's read as the set of all ordered pairs x and y. What does this bar mean? Such that, good, x is equal to the absolute value of y plus 2. So now, visually, what happens when you flip the x and the y, instead of thinking of the y-axis as instead of thinking of the y-axis like you normally think of it as, and the x-axis, they flip, right? So you're thinking of the x-axis as your y, and you're thinking of the y-axis as your x in terms of navigating. So typically, if we're thinking of this is an aside, okay? This is an aside, just thinking out loud. This is an aside. The absolute value of x looks like a what? I'm going to count to 3, draw it in the air. 1, 2, 3. Good. It's a V. Good. It looks like this. It looks like that. Centered at the origin though, right? It looks like that. Okay? That's how we normally think of it. And what does the plus 2 tell us to do on the outside? Up to, right? So we would typically take that and, as you said, shift it up to. And this is the absolute value of x. This is the absolute value of x plus 2. And now we're saying that our function is x equal to the absolute value of y plus 2. So what we're thinking of now, we're thinking of this as our navigating point. So our absolute value is facing this way, right? To the side, good. Like a Pac-Man, to the side. And then we're going to shift it to the what?
To the right.
To the right, good.
Wait.
So we shift it to the right.
What made it turn again?
The fact that you flip the x and the y.
You switch the X and the Y.
Oh, for the inverse.
Yeah, yes, for the inverse. So now I'm asking you to graph the inverse. So it helps to understand how it is when we originally think of it, and then remember in our minds whenever we actually looking at the inverse, where our axes are flipping.
So if they're flipping, why wouldn't it just be upside down? If it's
They're exchanging. We're exchanging them.
because if you flip it upside down, it'd still be on the same spot.
So yeah, in terms of the words we're using, we're not, I can be more clearer. We don't want to say flip, we want to say exchange. We want to exchange them. Bless you. Does that make sense? Bless you. Okay, so our question now is, what is our domain of this inverse function? What's our domain? In interval notation.
Is it negative infinity?
So you're saying these numbers are possible?
No.
No. Oh, 2.
What goes at 2?
Bracket.
Bracket, good. Bracket 2 to
Infinity.
infinity. What goes at infinity?
Parentheses.
Good.
Union.
Union?
No.
Or is that it?
I'm asking.
I think that's it for domain.
That's it for domain.
Oh.
That's it for domain because you already said take 2 to infinity. Why did we say 2 to infinity? Because this is where it started for all possible x values, and it goes out, oh, come on, catch up. It goes out to infinity. Okay? What's our range? What are the possible y values in interval notation? All real numbers, and in interval notation, how do we say that?
Isn't it the XER with the double R?
No, not XE double R. You can say all real numbers this way. What you're saying on the side is X belongs to real numbers, but it's not just X. We have order pairs. So we have to be careful there.
Can you also
In interval notation is what I'm asking for.
Oh. Negative infinity to infinity?
Good. Or good, negative infinity to infinity.
That's all I was gonna ask
You got it. Good. What questions do you have? Okay, so now we have the horizontal line test. We talked about the vertical line test before, and that helped us determine whether our function was indeed a what? A function, right? It could not touch the graph in more than one spot. So now we're learning about the horizontal line test and what it's good for. So let f be a function. We say that the graph of f passes the horizontal line test. The horizontal line test if every horizontal line in the plane intersects the graph no more than once. Okay? The horizontal line test is helpful. So let's say something else first. If f passes the horizontal line test, then f inverse is also a function. So the horizontal line test is helpful because if our original function passes the horizontal line test, then that tells us that when we look at the inverse, it's also a function. Okay? So a definition. A function f is 1 to 1, is 1 to 1, if for every pair of distinct elements, x1 and x2, in the domain of f, we have f of x1 does not equal f of x2. So if we have two elements, x1 and x2, in our domain, that means those elements have to be different in our range. If we take two elements in our domain that are different, that means the elements, what they map to have to be different. Okay? This means that every element of the range of f is paired with exactly one element of the domain of f. Okay? All right. So we have some definitions. Back to example part B. Yep. So this one, the actual inverse, would pass the horizontal line test. Because you would take this, so for each x, there would be one y.
But if it was originally, like if we were to graph the original function, wouldn't that fail the horizontal line test then?
Yes, so it does. That's a good question. So we're looking at, in part A, we were looking at just the relation. It's a good question.
Yeah.
It's a good question. It's a small thing, but it's an excellent observation to make. When you went back to example 1, you were like, wait a minute, we started with the absolute value of x. Why did it have an inverse? Because we were looking at it as a relation only. Now we're trying to determine if the inverse is a function. Different questions. Good question. What other questions do you have?
So the relation with
In example 1, yes.
so what was the relation?
The set, we had to write down the relation for the inverse. The inverse of a relation. That's what we did here. What other questions do you all have? What? Okay. Now let's make sure we understand a couple of more things before we look at some examples. So you need to know these facts. 1, the inverse, this is read as what? How do we read this?
Inverse.
F of -1.
We don't read this as f of -1. This is what?
The inverse of F.
The inverse of f. Good. This is the inverse of f. The inverse of f of a function, f, is also a function if and only if f is 1 to 1. That's important. The inverse of f, the inverse, f inverse of a function is also a function if and only if f is 1 to 1. Okay? If you have the graph of f, then f is 1 to 1 if and only if its graph passes the horizontal line test. If you have the graph of f is 1 to 1. If you have the graph, f is 1 to 1 if and only if its graph passes the horizontal line test. Okay? So, we're going to determine now if the following functions have inverse functions. We're going to determine if the following functions have inverse functions. We're going to determine if the following functions have inverse functions. F of x is equal to the absolute value of x. Remember, if you need to send a message, step out in the hallway. F of x equals the absolute value of x. Does this function have an inverse function?
Yes.
I see some heads shaking no, some yes. How do we check? How do we check? Thinking about those two facts we talked about, how can we check?
Plug in numbers.
What tests? You can also plug in numbers.
Horizontal line test.
Horizontal line tests, what are we looking for?
To see.
So I didn't get that far.
What are we looking for if we use the horizontal line test?
To
You got to
see
think
if
it
the
through.
X is repeat.
To see if what?
If the X is repeat.
If-
Or if it passed the vertical line test.
Are we're
the
thinking,
horizontal line test.
So does the-
what's your it?
If the X's, because it's a function if the X's don't repeat. So,
What's a function?
the absolute value of X.
Are we trying to determine if the absolute value of x is a function right now?
No, we trying to see if it has if it's the inverse, if the inverse is a function.
Yeah, we're trying to determine if this function has an inverse function.
Right.
So you said we use the horizontal line test. So we look at what? We use the horizontal line test for what? So you're saying we graph what?
The absolute value of X.
Okay, so good. I agree with you so far.
Right.
We graph the absolute value of x. We can make it look a little better. We graph the absolute value of x. Now what?
You see if it passes the line test.
Which line
The
test?
horizontal line.
So we take, let me use, what color? Red?
Red.
Red is going to be our horizontal line. Does it pass the horizontal line test?
No.
No. This does not pass the horizontal line test in those 2 points exactly. So specifically these 2 points. So this does not pass.
It's because they share a lot, right?
Say it again.
Because they share a lot.
It's because, that's a good point. It's because whenever you have 2 different x values. Sorry. Go.
I was trying to figure out.
I am very different. I'm a different kind of professor. When I hear noises like this, I'm thrown off completely. Okay? Okay, so so once you have 2 different x values, right? Those 2 different x values should have different what values?
Why?
But as you just pointed out, they have the same y value. So because 2 different x values have the same y value, that means it does not pass the horizontal line test. Or in other words, that is not a one-to-one function. Does that make sense? So if you had different y values, then you'd be good as long as those x values were different. So this does not pass. I'll give you 1 second. Let's finish this. This does not pass the horizontal line test. Okay? Which means here in part 2, or we could look at part 1. We're using the graph. So it says if you have the graph of f, we graph the absolute value of x, then f, this function, the absolute value of x, is 1-to-1 if and only if its graph passes the horizontal line test. This does not pass the horizontal line test, which means the absolute value function is not 1-to-1. And we know that the inverse of a function f is also a function if and only if our original function is 1-to-1. These are failed.
Right.
Now go ahead.
So 1-to-1 would mean all the x's are different, all the y's are different.
You have to say it a little bit differently. For 1-to-1, for any 2 distinct x values, the corresponding y values are also distinct.
Meaning they're different.
Yes,
Okay.
So basically.
for any 2.
Concept as vertical line test, if your x value repeats, it's not pushing.
Swapped,
If
yes,
your y value repeats, it's not pushing.
right.
Like,
But we have to, it's different because you're saying for every x there is a y. But you're saying for your vertical line test, you're saying for every specific x there's one y. But for this, you're saying for any 2 x's, the 2 y's have to be different. If for any 2 different x's, the 2 y's are also different that correspond to it. The values are different. Vertical, when you have a vertical, different color just to answer your question. If you have this parabola, for example, and you're thinking of the vertical line test, you're taking that vertical line, this red line, and you're moving it over on this graph. So for every x, you have exactly 1 y. That means this parabola is a function, right? So for each x, you have 1 y, but for the horizontal line test, for any 2 different x's, you do want it to be where you have. So we're going to go through an example next. You're trying to determine what about its inverse. So if you're looking at the horizontal line test for the same one, it wouldn't pass it. Right, because the y repeats for 2 different x's. So, yes.
So like the negative x and the positive x will have the same y, which make it not.
Which makes it not 1-to-1. You got it. You got it.
So, I guess I'm confused about if there's ever a situation where an absolute value would still have an inverse. Because when we did the other, like example 1,
Yep.
it was the absolute.
All right. So let's summarize. So this is one way of looking at this. This does not pass the horizontal line test, so we can conclude that f of x does not have an inverse. Another way, an alternate way, Kelly said that we could choose values, right? An alternate way. So note that if we choose 2 distinct x values, -4 and 4, note that -4 is not equal to 4, right? So according to the definition of 1-to-1, that means that if we choose 2 distinct values, then the corresponding y value should also be different, right? So that means whenever we look at f of -4 and when we look at f of 4, we're hoping they're different. F of -4 is what? 4, because it's the absolute value of -4. That's 4. What's f of 4? 4. Are they different? No, they're not the same, right? So you have Negative 4 is not equal to 4, but f of negative 4 equals f of 4, which means f of x is not what? What's the word that we learned?
Inverse.
Look on the previous page. What are we talking about? Oh, okay, good. F of x is not 1 to 1. F of x is not 1 to 1. And consequently, we know if f is not 1 to 1, that means what about inverse?
It's not.
It's not an inverse. You got it. So f of x does not have an inverse. So that we know. So there are two different ways of doing that. Okay? Part B. I've given you the graph. And now you know how to do the graphs at this point. If I give you g of x equals x minus 2, quantity cubed minus 1, what's your parent function? X cubed. You know what x cubed looks like. It looks like that, right? And so you take that, the minus 2 on the inside says you go what? You go right 2?
Yes.
So we go right 2, and the minus 1 on the outside says we go down 1. Good. So this is the graph of x minus 2 quantity cubed minus 1. Question is the same. Determine if the following function has an inverse. Does g of x have an inverse?
Yeah.
Why?
Because it passes the horizontal.
You got it. Good. So g of x passes the horizontal line test. So that means g of x has an inverse. We've answered our question. What questions do you have?
So can you explain that, as the neighbor four is absolute value?
I can't hear you.
Can you explain that, neighbor four equals absolute value of neighbor four?
Sure, we were checking to see if our function, so he's back on part A and asking a question about part A. So he wants me to explain this part. So the reason why we're saying this is because we need to determine if this function has an inverse or not. So it says the inverse of a function f is also a function if and only if f is 1 to 1. So we have this function f of x. And if we see f is 1 to 1, then that would mean that f inverse is also a function, which is really our question. So we're checking to see if f of x is 1 to 1. So we chose two distinct x values, and we need to check to see if the corresponding y values are also distinct. F of negative 4 means we plug in negative 4, or we substitute a negative 4 for x here. We get the absolute value of negative 4 is 4, because the distance from the origin is 4 units, no matter if it's to the left or to the right. And so f of 4 is the absolute value of 4, which is also 4. These two are different, which means they're distinct. Or no, I'm sorry. These two are the same. 4 is equal to 4, right? Because we got the same number, that means this function is not 1 to 1 because these are the same.
And you go back to the horizontal line.
Yeah, yes, you could use this graphically, pick graphically, the way the visual representation of it, you can think of it this way.
So
You can choose this is negative 4, this is 4, and then this would be 4.
So let's say like the 2 dot, red dot, these are 4.
Yes, this would be 4 and 4. So what you need to be able to do is go from the graph to the algebra, right? This is the algebraic way. This is the graphical visual representation of it. That's good. So this would be, as you pointed out, that would be negative 4. This would be 4. However, both of these are at 4 there. Good.
So can you draw one that would pass and one that wouldn't pass?
This is the example.
Oh yeah, my bad.
That's the example. What other questions do you have? Okay? All right. Going back to this one. If we restrict its domain to 0 to infinity, meaning we ignore this side, if we ignore this side of the graph, then our new function will be 1 to 1, right? Because we won't have the left side of that v. Okay? So, a couple of notes. If we restrict the domain of f of x in example 2a, so if we restrict the domain of f of x in example 2a to 0 to infinity including 0, then the new function is 1 to 1 and it has an inverse function. The restriction of the domain changes the function. That's important to note. The restriction of the domain changes the function. Okay? These are important to note. I'm saying that. These are important to note. I said it 3 times now. Okay? A cloud. This is important because you need to know how to find the inverse of a function algebraically. This procedure will always be the same for you to find the actual inverse of a function algebraically or mathematically. How to find the inverse of a function. Let f be a 1 to 1 function. So we have to start out with what kind of function? It has to be 1 to 1. You need to confirm that before you even start finding the inverse. Are we clear? Let f be a 1 to 1 function. You have to make sure f is 1 to 1 before you even begin.
So that should be our first step.
That's what I'm saying. Okay? Good. Yes. So let f be a 1 to 1 function. And assume that f is defined by a formula. To find a formula for f inverse, 1, we replace f of x with y. 2, we solve the equation for x. 3, we replace x with f inverse of x. And 4, we replace y with x. You need to know this. This is the process. Let's apply it. Cancel. Okay? Find the inverse of the given function. What do we first have to check for g of x? If it's a 1-to-1 function, let's examine g of x for a minute. What kind of function is g of x? Say it again. It's linear, right? So it's a what?
1 to 1.
No. Yeah, it is going to be 1-to-1, but it's linear, which means the graph is a line. Okay? The graph is a line. So this is us checking, doing a visual representation. It's the graph is 4x shifted up or down?
Down.
Which one? I heard up, I heard down.
It's -3, so down.
It's -3, so down. Good. It's a line, not a curve. Okay? So 4x minus 3, it's a line. So it is 1-to-1 because it passes the horizontal line test. Note we check first. Again. So g of x is, we conclude g of x is what? 1-to-1. Good. G of x is 1-to-1. Okay? G of x is 1-to-1, which means we can go ahead and we can find the formula for its inverse. First step is to do what?
Replace f of x with 1.
Instead of f of x, we have?
Y.
Instead of f of x, we are given g of x. So what does our function now become?
Y.
Good. Y equals 4x minus 3. That's step 1. Now what do we need to do?
Solve the equation for x.
So go ahead. How do we do that?
Plus 3.
Add 3 to both sides to get y plus 3 equals 4x. Now what? Say it again.
Divide by 4.
Good. Divide both sides by 4. So we get y plus 3 over,
4 is equal to x.
good. Now what do we do?
Replace x with the inverse.
With f inverse of x?
Yeah.
Replace that with f inverse of x. Good. So we have y plus 3 over 4 equals f inverse of x. Now what do we do?
Replace y with x.
You got it. So tell me what we have.
X plus 3 over 4.
X plus 3 over 4 equals f inverse of x. Good. That's it. So we found the inverse of the given function. We found the inverse of the given function. We found the inverse of the given function. What questions do you have? Let's look at another example. You want to look at another example, or are you good with that?
Another example.
Okay. So we found the inverse of the given function. You can take a picture of it. Okay. So we have f of x equals the quantity x minus 5 cubed plus 2. What do we need to check first? Is it 1 to 1, right? So you said our parent function was what?
X cubed.
What do we do with it?
Graph.
Yeah, we're going to graph
Oh,
it.
sketch it.
Yes, but I'm asking you, what does our function say we do with x cubed?
We go right 5 up 2.
Right 5 up 2.
She's trying to do it. Okay.
Right 5 up 2. Okay? Okay? What can we conclude?
It passes.
It passes. So f of x passes the horizontal line test. What can you conclude? Very good. So f of x is 1 to 1, which means we can find its inverse. So let's go. Tell me what to do.
Y equals x parentheses x minus 5 over 2 plus 2.
Good. Somebody else tell me what to do. Subtract 2. So you get y minus 2 equals what?
X, what? Parentheses X minus 5 cubed.
Good. Now what do we do?
Take the cube
Take the
root.
cube root.
Take the cube root. Good. We now take the cubed root of both sides. So we have the cube root of y minus 2 equals the cubed root of the quantity x minus 5 cubed. Now what do we get?
No, the cube root of y minus 2 equals X minus 5.
Good. Now what do we do?
Root of 5.
What to get?
Cube root of y minus 2 plus 5 equals X.
Good. Now what? Somebody else pick it up from there. What do we do?
Connect to the inverse.
We do what?
Replace x with the inverse, the f inverse of x.
That's right. And I'm pausing because I want you to be able to say it. Yes. We replace x with f inverse of x. You got it. So this gives us the cube root of y minus 2 plus 5 equals f inverse of x. Now what? Replace y with x, so we get what?
Cube root of x minus 2 plus 5.
All of that plus 5 equals
inverse of x.
You got it. That's it. That's it. That's the process. That's how you find a formula for the inverse of a function. You have to make sure you have a one-to-one function. If you have a one-to-one function, you smooth sailing. Okay? If you don't have if you do not have a one-to-one function, that means there is no formula for the inverse. Okay? All right. So a theorem here. Composition of functions and inverses. Given a function f and its inverse, f inverse, the following statements are true. F composed with f inverse of x is equal to x for all x in the domain of f inverse, meaning x has to first go into f inverse. And then f inverse composed with f of x is equal to x for all x in the domain of f. Okay? So, things to note here. Some things to note. Does it seem confusing with the notation? Or you're good with the notation?
What do you mean, like?
The composition, the left-hand side, are you good with that? I see some shaking their heads yes, some saying no. Are you good with f of g of x? This is the same idea. So let's just remember that whenever we are thinking of an inverse, think about if you multiply, let's think about numbers for a minute. If you multiply 5 times 1/5, what do you get? 1. If you multiply 4 times 1/4, what do you get? 1. If you compose a function with this inverse, you get it should be the identity. So whatever your composition is of x should be x. That's the same idea. Okay? That's all this is saying. That's all this is saying. Okay?
X, or all x in the domain.
Okay, so yes, you all are reading this. If you look at f composed with f inverse of x, that equals x, and f inverse of f of x equals x, then you're looking at the domain x here in f inverse, the domain x for x in the domain of f here, but you're not getting the same function. That means when you compose them, you get the identity element back, and that means those two functions are inverses of each other. That means those two functions are inverses of each other. That means f and f inverse are inverses. So this box, whenever you check both of these, that gives you that f and f inverse are inverses of each other. So we're going to verify that f composed with f inverse of x is actually equal to x, given those two functions. Given those two functions, we just want to confirm that f composed with f inverse of x is equal to x. This is what we aim to confirm. So, f of x is equal to x, the quantity x minus 1 cubed plus 2, and f inverse of x is equal to, you can say the cubed root if you don't like this. If you don't like this, you can write the cubed root. Do you prefer the cubed root?
Yes.
Then what you can do if I give you that is rewrite this as the cubed root of x minus 2 plus 1. So if you don't like it the way that I gave you, you can actually rewrite that. You need to be comfortable with either one. Okay? So we're checking f composed with f inverse of x. We want it to be what in the end? What do you mean by the same? What do we want it to be? We're verifying that it's going to be what?
The domain of
That
What does the question say? We're verifying what?
that L
Composed with?
composed with the f inverse of x equals x.
So whenever we look at this, ultimately, whenever we do our justification, we're hoping we end up with what?
the same.
What do you mean by the same? We hope we end up with x. Yes, we hope we end up with x. So we have to confirm that. So the first thing we have to do is do what here? Put in what?
The equations, plug in the equations.
Plug
So,
f of the inverse of x into
F inverse of x.
f inverse of x into f of x?
Yes, that's what we have to do. And so what is f inverse of x?
Cube.
Talk loud.
Cube root x minus 2.
The cube root? Go ahead. Of x minus 2, you said?
Yeah.
Okay, go ahead. Plus 1. So that's f inverse of x. So we took that, and now we need to find f of that. So now tell me what we do. What are we going to do? We're going to take this and do what with this?
Plug it into the
F of x.
f of x.
Right, for,
X.
that's right.
X value.
That's what we're going to do now. That's what we're going to do now. So, tell me what we write.
F.
We write f again?
No. We write the cube root of x minus 2 plus 1. Don't we put that in parentheses?
You got to tell me where you want parentheses if you want them.
At the beginning, in the end, minus 1. And then, wait, all that's supposed to be cubed. So,
Where do we put another set of parentheses
at
at?
the beginning, and then at the behind the minus 1.
Right. And what do we do with that?
Cube.
Cube it, yes.
2.
You got it. Absolutely correct. That's what we do. So, tell me what you do now. Simplify inside the parentheses. You got it. What do you get when you simplify inside the parentheses? Cube root of x minus 2. And what happens with the rest? They cancel out because you can drop that inner set of parentheses and you have plus 1 minus 1, all of that cube plus 2. So that means this plus 1 and that minus 1 cancels out. So you get, as you said, the cube root of x minus 2, quantity cubed, plus 2. What's the cube root of x minus 2 quantity cubed? X minus 2, because this, that cube cancel, as you were saying. Good. So you get x minus 2 plus 2. What happens? You got it, and you end up with? That's it. Okay? In a similar fashion, so we've shown what we aim to show. We showed that f composed with f inverse of x was equal to x. That's what we showed. We can also show that f inverse composed with f of x will be equal to x. You can do that on your own time. Confirmed that's true. This will mean, according to that box on the previous page, this means, remember, if you need to send a message, go out in the hallway. This means f and f inverse are what? According to the box, the same?
Different.
No, go look at the box on the previous page. Does it mean they're equal? What does that box say?
Or x.
F and f inverse are what? This means f and f inverse are actually inverses. What questions do you have? Okay, so we're going to cover 6.1. 6.2 is extremely short. It's polynomial long division, which is something you've done before you came here. Just showing you a shortcut. It's showing you a shortcut to that. And we're going to do 6.1 and 6.2 on Thursday, possibly get to 6.3. So make sure you print out all of your notes for 6.1, 6.2, and 6.3 for Thursday. We're going to go through that. Make sure you come prepared because we're going to move. Your exam is next week, next Thursday. Watch them out. It's next Thursday, okay? Next Thursday, I won't be here. I'll get someone to proctor the exam for me. I have a conference, okay? So you have that coming up. I will have an extra review session for you, okay? Yes.
About the quiz.
The quiz is gonna open today. You'll have 24 hours for it.
So tomorrow 5.3 is due, 5.4 is due, and the quiz?
What we've done, the dates, yes, you have 24 hours for 5-3. That you all knew. I told you all that last week. We've done 5-3. We finished 5-3, 5-4. I can change those dates to Thursday.
Yes, please.
Okay? But the quiz is remaining 24 hours.
So we just doing 5-3.
What?
We just doing 5-3.
No, I think she means 5.3.
The quiz you do, I'm going to change the homework due dates for Thursday.
For
Okay.
5.3 and 5.4?
Yes? Yes. What other questions do you have? All right, y'all have a good day. See you Thursday. Make sure you come ready. I'll hand your group work back to you on Thursday. If you came in late, see me now.